Hello everyone. In this video, we are going to discuss the part B of practice exercise 2.1 from your chapter 2, that is coordinate systems and transformation. So for part A, I have given the link in the description box. You can go through that one. Now in the part B, we are going to transfer the given vector into its cylindrical as well as the spherical coordinate system as stated. So very firstly, we are going to write what is given to us, and for your reference I am going to put what are the necessary equations, or you can say the parameters which will be we are going to use throughout this numerical. So I am also going to put that one, and then we will discuss on to that one, and then we will simplify the given numerical. Okay, so we will start with what is given to us. Okay, so this is the given vector, and if you look out for the given vector, you can see there we have the given vector in its cylindrical, sorry, in its Cartesian form, or in its rectangular form, since we have the components along x and z direction. So if you are going to rewrite this given vector for its rectangular form or Cartesian form, so what we can write? We have this, that is qx ax plus qy ay plus qz az, where capital Q, X, Y and Z, they are nothing but what? Components along your unit vectors, that is ax, ay and az. So say this to be equation 1. Okay, fine. So we will rewrite that again. Okay, so this is your given equation in its Cartesian form. Now if you are going to compare the given vector with respect to our this standard vector, so you can find that there is no y component over here. Okay, so we have this term, that is qy and ay, which is equals to 0. Now if you are going to rewrite this equation, so what we have? We have the given vector, that is vector q, for its x and z components only. Okay, so we have this given vector in its x component along x direction and its z component along z direction. So say for this is your equation 1, and this as your equation 2. Now if you are going to compare this equation 1 and 2, so you will find this magnitude over here is what? It is component along x direction, so we can say this to be the qx, and this component along y direction is said to be the qz. So don't worry, we are going to rewrite this equation again. So this is for your reference purpose, that we have qy ay component to be 0. Okay, now we are going to rewrite what is the necessary expressions in order to convert this given Cartesian coordinate system into the cylindrical one. Okay, so these are the two expressions that we will be using for your this numerical. So very firstly what we have, so if you look out for the very first bracket, if we are given with the uh, rectangular systems, so we can convert that rectangular or Cartesian system into its cylindrical form. So we are, if we have that x, y and z, so we can convert that into the row phi and z. And this second table is second box is for your uh, vector transformation from cylindrical one to the rectangular one or Cartesian one. Okay, so we are going to use this to one. Now if you look out for your given vector, so we have that vector q is equals to square root of x square plus y square divided by square root of x square plus y square plus z square. Now we are going to replace that values with respect to your this values over here. So what we have for your square root of x square plus y square over here, this one, so we can rewrite that square root of x square plus y square as rho. So we have this very first value over here for your square root of x square and y square. Okay, so rewrite that one. So your given vector q, it will be what now? So given vector q will be square root of x square plus y square. We have that to be the rho over here. So put that rho within your given vector expression. Now square root of x square plus y square, again that we have to be the row. So that value you can say over here, this to be the row square. So that's why we are going to rewrite that square root of x square plus y square as row square. Then this ax will be as it is over here, then minus. So what we have for y? So we, for that y, we have that to be the y is equals to rho sine of phi. So rewrite that one. So replace that y by using that rho sine phi. So we have that rho sine phi for your y value, and z will be as it is again divided by square root of x square plus y square is what? What we have written for that one. So that is rho square, and this z square will be as it is, and this az will be as it is over here. So this is your value of, or you can say this is your vector for in terms of values for that rho phi and z, but still we have that ax and az component over here. Now next is what we are going to compare this given vector with respect to your previous equation. So this is what we have, equation 1 and 2. So now your equation 1 is what? So we are going to say this to be here as your equation 1, or for your reference I'm going to say this to be the equation 3 now. Okay, so we are going to compare equation 2 and 3, equation 2 from this slide. So we are going to compare this equation 2 with respect to your equation number 3. Okay, sorry, my handwriting is not as good as yours. So we are going to compare equation 1, sorry, not 1, equation 2 and equation 3. So what value you will find for that? So you can say that qx is what we have. Qx is what? Rho divided by square root of rho square plus z square, and we have qz. Qz is equals to what now? Rho sine phi z divided by square root of rho square plus z square. Okay, so this is what we have, and this is to be given with the minus signs. Why? Because we have written plus over here, isn't it? So that's why we have that qz to be the minus of rho sine phi z divided by square root of rho square plus z square. Now next is we are going to make use of the vector transformation table in order to have that multiplication over here. So for your reference, again I am going to put that table so that you will not get confused. So now we will write for that vector transformation table. Now to convert this this Cartesian system into cylindrical one, we are going to make use of this vector transformation table, where we have the dot operator and its x, y, and z component, and r, phi, and z component over here. So this is not actually r. You can say rho for your reference purpose. Okay, so this is rho, phi, and z. Okay, so we have this vector q in terms of its cylindrical form, that is q rho a rho cap plus q phi a phi cap plus q z a z cap. Now what is that q rho? So q rho is nothing but what? It is component of vector q along rho direction. So you can refer my previous lectures as well, where you can get the idea of this, what exact is this q rho, or you can say any of the vector along with its suffix, that is rho. So this q rho is nothing but what? Given vector q. So this is what is your given vector q along the rho direction. So we have that vector q, that is your given vector q along rho direction or along unit vector rho. So what is that vector q? So you can refer this previous slide as well. So this vector q is this one, your equation 2, which is nothing but what? Qx, ax plus qz and az. So we are going to put that value over here. So your given vector q is what? Qx, ax cap plus qz, az cap. And it should have to be dot or dot multiplied with respect to your unit vector arrow. Okay, now we are going to make use of this vector transformation table over here. Okay, so we have that qx, this ax dot arrow. So what we have for this, for your reference, I am going to write over here. So ax dot arrow. So what we have, ax dot arrow is to be what? Cos of phi. So we are going to write that to be qx. Let me rewrite it for you. Well, I hope you are getting this point. So this qx is what? Ax dot arrow. So what we have? Ax dot arrow is equals to what? We have that to be the dot product equals to cos of phi. Then plus sign will be as it is for now. Then we have the qz as it is for now. See, if you have enough practice, directly you can put that values, but I'm considering you as new to this one. So that's why I'm going into the details. So if you find this video to be lengthy, you can go with the increased speed of this video. Okay, now we will multiply that one. So az dot arrow. So what we have for that, az over here, and this is arrow over here again. So az dot arrow is what? We have that value to be equals to 0. Okay, so what is the ultimate value for your q row? So q row is equals to what we have. So qz dot 0 is equals to what? We have that to be the 0. So we have this value to be qx cos of phi. Okay, so this is your q row. But what is qx? So if you are going to compare, so you can refer this slide over here, where we have compared equation 2 and equation 3. So we have that qx is equals to what? Rho divided by square root of rho square plus z square. So put that value over there. So we have that q rho is equals to qx. So what is the qx that we have from the previous slide? So that q rho is equals to rho divided by square root of rho square plus z square into cos of phi. So this is the very first element that we have from our equation. So you can have note for that one. Sorry. So this is the q row. You can note it down. Okay. Now in similar fashion, we are going to find out what is that q phi and that qz over here. So what is that q phi and qz? So you can pause the video if you are enough confident, and if you are not confident, then you can follow me this one. So we are going to find out what is that q phi and qz. Okay, so we will find what is that q phi. So what will be the q phi? So q phi will be again your given vector q having the dot product with respect to your unit vector along phi direction, that is a phi. So we have that vector q to be what? It is again same as the previous one, so that is qx ax cap plus qz az cap having the dot product with respect to your a phi cap. Okay, so very firstly we will have the multiplication, and then we are going to put the values as we have done here in this case. So qx, for now I am going to put it as it is for your reference purpose. Now the dot product in between this ax and that a phi, ax and that a phi. So what is that one? So we have that ax over here, that is ax and then a phi. So a phi over here. See, you can see over here. So you just go by this way and this way. So the dot product in between that ax and that a phi is what? Minus of sine phi. So the dot product in between that ax and a phi is what? Minus of sine phi. So place that value over there, sine of phi. Then the dot product in between that az and a phi. The dot product in between az over here, az and a phi again over here. So go by this way, dot product in between that az and that a phi is equals to what? We have that to be the 0. So I am not going to write that one again in detail. So simply we are going to put that value to be 0. So what value we have from this for your q phi? So we have that q phi is equals to what? Minus of qx sine of phi. Okay. Now what is the qx that we have from the previous slide? You can refer that one, or you can simply make use of this. So qx is what we have, that is equals to, sorry, this is not theta, so this is your q phi, place the value of that, this minus sign will be as it is qx. So qx is what we have, rho divided by square root of rho square plus z square and then this sine phi as it is over here. Okay, so this is what we have for that q phi. Now next we are going to find out what is that qz. Okay, so qz we are going to find out again. For your reference purpose, I am going to put this table everywhere so that you will not get confused with respect to that dot product, and you can have the note for that x, y and z values that we have discussed earlier. Okay, so qz will be what now? Your given vector q having the dot product with respect to the unit vector along z direction, that is az. So we have that vector q to be what? Qx ax plus qz az having the dot product with respect to the az. Okay, now have the dot product. Well, I hope that at this moment you have come to know about what is the dot product in between the given two unit vectors, that is ax and az here in this case. So dot product in between ax and az is what we have. This is ax and this is az. So we have that value to be the 0 over here. So this term will be, very first term will be 0. So I am not going to write into the details. Well, I hope that you came to know about this one. Then we have the dot product in between that az and az. So we have this az over here and again az over here. So over here. So the dot product in between the two same vectors is what? We have that value to be 1. So what is left over here? Az dot az is equals to 1. So we are left with the qz only. See, if you have enough practice, so you can directly say that qz is equals to qz. That means this value will be as it is. And what is that qz? You can refer this previous slide. So we have this qz is equals to this one, minus rho sine of pi z divided by square root of rho square plus z square. So you just put that value over here for your qz. So we have that qz is equals to what? Minus rho sine phi z divided by square root of rho square plus z square. Okay, so this is what we have for that rho, phi and z. Now you can put this value in your equation or expression that we have written over here, over here, yes, over here. So you just simply put the values of that rho, phi and z to get your answer in its cylindrical system. So let's rewrite this one again, rho, phi and z. So we have that vector q is in its cylindrical form, which is equals to q rho a rho, then q phi a phi plus qz az, which is equals to, so this is vector q. So q rho is what we have that to be the rho divided by square root of rho square plus z square cos of phi a rho plus q phi. So q phi that we have to be the minus of rho divided by rho square plus z square. So I'm going to rub this one. So q phi we have that to be the minus of rho divided by square root of rho square plus z square a phi plus qz is over here again. So that is again minus of rho divided by square root of rho square plus z square. So this is what qz is minus of rho sine phi z, and here this q phi is what again? So that is again minus of rho sine phi, minus of rho sine phi over here. Sorry for that. Okay, and what is left? Yes, is it? Is it? Now, if you carefully observe for your this given vector q in its cylindrical form, you will find that this rho divided by square root of rho square z square is common everywhere, isn't it? Over these places. So we are going to rewrite this where your vector q by separating that one, so that we will have the final answer. So your given vector q in its cylindrical form will be what now? That will be rho divided by square root of rho square plus z square, and so we have taken it as common. Now you can rewrite within that bracket what is left. So what is left from your very first term? So we are left with the cos of phi a rho minus sine of phi a phi, then minus z sine phi, z sine phi, sorry, z sine phi is z. Okay, so this is your final answer, that we have converted the vector q which was in the Cartesian system in its cylindrical form. Okay, so this is your final answer. Well, I hope you have get some understanding from this numerical. In the next video, we are going to see the conversion of this Cartesian system of vector q into its spherical form. Okay, so if you get some understanding from this video, so just hit the like button, and if you have some feedback for me, so write it in the comment box. Okay, so thank you for now. See you in the next part of the same video.